Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Shanmugha Balan and Khushboo Rao with us today. Hello, Balan and Khushboo.
Thank you, Frank, for giving
Hello.
us opportunity to talk
Just
here.
about your very lovely article on this November 19th of 2024 as we record this, and we will get to that real soon. So Khushboo, let's start with you. What's your geolocation? Where are you at?
Right now, I'm in Taiwan. I'm doing postdoc at National Central University, Taiwan, Astronomical Institute of Astronomy.
Mhm.
So currently, I am working on variable stars and particularly open star clusters.
Okay.
And so I
Cool.
joined here. It's been a year. Here I joined. This is the same day when I joined NCU last year,
How
20th
about that?
November.
So it's a birthday.
Congrats.
It's a
Congrats on the
birthday.
Yeah.
anniversary.
It's a birthday. Very
Yeah.
good.
And I did my PhD from Birla Institute of Technology and Science, Pilani,
Very nice.
and I graduated in 2023, and then I joined here. So there I worked on blue straggler stars, and now I am working on open star clusters,
Okay.
the
Very nice.
whole and the variable stars and those things.
Cool. Very cool. And Balin, how about you? Where are you located at?
So I have a bit of a complicated story. When people say where you're from, that's a tough question.
Okay.
So let's begin with first where I was born, which is in Chennai. I spent most of my school life over there.
Okay.
Then I moved on to Pilani, where I did my undergrad from the Birla Institute of Technology and Science, Pilani.
Uh-huh.
That's where I met Khushboo and all of the other co-authors of this paper. Not all, most of the other co-authors of the paper.
Got it.
And I graduated a couple of weeks ago from my undergrad, and now I'm in Hyderabad. I'm working for Micron Technology, which is a
Cool.
Boise-based semiconductor company.
Very nice. Very cool. Very cool. Let's see. And it is November when we're at. We're certainly past equinox. In fact, solstice will be coming up. So, do we have winter where you're at yet, or is it still fall in Taiwan?
No, here it's
It
a
is winter.
Winter. Oh,
yeah,
very
definitely
good.
here also.
It is winter. It's 20 degrees Celsius, which I don't think a lot of people Celsius, which I don't think a lot of people find cold, but I find it cold. So
I
Yeah,
would
same
find
here.
that
It's
cool.
also
Yeah. So I'm in Phoenix, and we are definitely in our winter mode. So currently we're dropping down fairly cool in the morning, but it warms up pretty good in the afternoon. So we get all the Canadian snowbirds coming down from Canada to enjoy the
southern weather.
winter in the desert. So very cool.
oh,
Very
that's
nice.
nice.
It's very good. And we already covered where you're at. And so let's go ahead and get into it. So we're going to do a little screen share of this very awesome AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Dynamical evolution of four old galactic open clusters traced by their constituent stars of Gaia, DR3, and Balan and Khushboo. Take us away.
So thank you, Frank, for the title. I think I'll just quickly begin by introducing the authors. So this was my second undergrad sub project or something of that sort. I started working under Dr. Kausha, the third author of the paper. She was my first foray into the field of research, and Khushboo was Kausha ma'am's PhD student. So that's
Got it.
how I got in touch with her.
Yep.
Both of them helped me a lot with this paper. Manan was my senior. He was also an undergrad at BITS, and so was Sauradeep.
Mm-hmm.
So all of us are undergrads, but Sauradeep at that point had already become a postdoc, and Manan, by the time this paper had come out, had started his PhD at Grappa and the University of Amsterdam.
Very nice.
So that's the brief background of all of the papers. Dr. Kaushar is all of our advisor.
Very cool. Very nice. Good shout out. Good shout out. Okay, let's go ahead and get into it. These four open clusters.
So, yeah, we picked four open clusters because a lot of studies in star clusters tend to be done based off globular clusters, and there are plenty of good reasons for that. But in general, our group has been one which focuses on and wants to study open star clusters
Uh-huh.
a bit more. So we picked four open star clusters: Berkeley 39, Columbia 261, NGC 6819, and NGC 7789. So we
Okay.
have some reasons which we'll get into it. But yeah, primarily we've been looking at blue straggler-based studies,
Ah.
and that's also been the focus of Khushboo's PhD. So I'll let her take it away for a bit, and before I join back.
Yeah. So basically, open star clusters or any star cluster which is older than 1 giga year, they have passed all the initial evolutionary stages. So
Yes.
now they are in the two-body relaxation stage,
Okay.
where the just long-term encounters and short encounters, the clusters is evolving. And they have at the time around 1 gigayear, they have many exotic populations too. And blue straggler stars are one of them. They form out of collision, merger, or mass transfer activities. So they are among the most massive stars
Yes.
of any star cluster. So as a cluster evolve, we know that because of the dynamical drag, the most massive stars settle in the cluster center prior to the any other cluster population. So
Yes.
this is the phenomena we were using to identify, to determine the dynamical ages of open clusters.
Okay.
But for these four open clusters, we have seen that when we compare their blue straggler distribution with different populations like red giant branch stars or main sequence turn of stars or main sequence star, they show different kind of um, signatures.
Yes.
So, but with blue stragglers, with RGBs, they are almost flat radial distribution.
Okay.
And that is why we wanted to take it up, take those four clusters to see how actually what is their dynamical status in compared to like other clusters or in a whole when we compare different populations with one another, what
Okay.
they show us.
Cool.
So because we have an advantage of having Gaia data, we have proper motion data, and also from many literature, we have radial velocity data.
Oh, nice. Very
So
good.
we wanted to see the spatial distribution of these stars
Right.
and the kinematical distribution, how they are kinematically distributed, because these clusters are older. So the energy equipartition will be effective here and will
Yes.
show some signature. And these signature will be useful to trace the dynamical ages of those clusters.
Very nice. Good.
So that is why we take it up this aim, and we aim these four clusters to study further to get to know more detail how blue stragglers are important or other populations are important and what signatures they do show in their features. Yeah.
Very cool. Very nice. Okay. Very good. Let's see. Want to talk about some?
So another specific thing which I'd like to highlight from the introduction is Ferraro et al.'s paper.
Yes.
So like I already talked about, most of the work in the past was looking at globular clusters, and Ferraro et al. Wanted to classify globular clusters into three different families. So we're looking at two different types of ages over here. One is the actual age of the cluster, which is given in giga years, while the
Yes.
second one is dynamical age, which is more of a parameter which we use to understand how much the cluster has evolved.
Yes.
And so Ferraro et al. Study classified globular clusters into three different families, 1 to 3 from young to old. And a lot of studies have, done a parallel study in open clusters, and we try to do the same using slightly different criteria and different parameters, but the same broad idea in the sense that we want to classify open star clusters on the basis of their dynamical age.
I'm with you. Yep. Very good.
So I think if we want to move on, we'll just briefly go through the rest of the paper. The second
intro?
section
How about
talks about
data?
membership identification.
Mm-hmm.
So membership identification was a fairly important aspect for our paper because we were very clear about wanting to study different populations in the stars, in the star clusters. So generally what a lot of membership identification techniques do is they rely on neural networks, especially the modern ones. They rely on neural networks or some sort of machine learning algorithm
Yes.
And the issue with some of these, despite being able to identify cluster members at very, very faint magnitudes, some of them go to excess of 20 mag.
20, yeah.
And the issue with that is they don't work so well in the brighter regions, counterintuitively.
Yeah,
So
that
we're
is
not able to look
counterintuitive.
at yeah, we're not able to look at the blue stragglers or the red giants or something of that sort. And we want to particularly identify red giants and so on, so that we can have a population to compare our blue stragglers with.
Okay.
So yeah, the things, if you scroll down to figure 2,
Yeah.
and the color magnitude diagrams, there's a very clear main sequence. And the issue which most neural networks have is that they fall into this sort of trap where they understand that the main sequence is a clear, nice, easy feature to latch onto, and that's where they look at. I'll just wait up for figure 2 to be brought in.
Yeah, we're going halfway around the
So
people, so we have a little bit of a bandwidth lag. So we'll just be patient on this figure 2 CMDs of these 4 clusters.
yeah,
It's all good.
so yeah, I mean, I'll just be talking about other stuff. So with blue stragglers, as you can see, compared to the main sequence, they're a fairly scattered population, very off to the side, which really does bring out the highlight of their extremely odd nature as compared to other clusters, which is why they're the primary focus of a study. And also the red giant stars, which are far off to the northeast of the cluster,
Yes.
at least in the CMD.
Uh-huh.
So by virtue of that, the main sequence is a very clustered, somewhat tightly bound, neatly organized structure. And most neural networks fall into the trap of, trying to capture that region very, very well. And they do their job very, very well. It's just that they're not able to figure out the other parts of the cluster.
Right.
And, there's a lot of other things there's a big tangent that I could go on to. But yeah, basically, we wanted a membership determination method that was able to focus on a broad overview of the cluster with respect to all of the specific different cluster populations that we want to take a look at,
Okay.
while also going down to fairly faint magnitudes. And MLMOC, I think, was Manan's work, which provided a very good balance in finding out different aspects of the cluster.
Okay.
So with MLMOC, we're able to identify these cluster members. The blue straggler specifically were one highlight which we wanted to pick, which brings me to the selection criteria. We wanted star clusters which have a fairly large blue straggler population. So all 4 of these clusters have a very, very clear and large blue straggler population.
Yes,
Then we also further divided the rest of the cluster into its different constituent populations.
Oh,
So
okay.
the regents, the turnoff, the upper and lower main sequence,
Okay.
which was a small criteria which we want to make. That's like fairly unique in the sense that I don't think there have been many studies in the past which have done something like this.
Yeah.
But the main idea was that heavier stars tend to accumulate towards the upper regions of the main sequence. So we wanted to capture the heavier stars separately and the lower stars separately because they're expected to have a slightly different kinematic behavior.
Oops.
So that was the idea behind this. And 6819 and 7789 also have a binary track, just slightly above the main sequence.
Okay.
If we draw a second isochron,
Uh-huh.
0.75 isochron as we call it,
Okay.
we can see that there is another extra track of stars which correlates to that isochron. So because with the clearly separable, these we call these the equal mass binary isochron, which
Yeah.
corresponds to stars which are of roughly which have stars of roughly equal mass within the binary system.
Okay.
So they're unresolved in the sense that if we look really closely, we cannot determine that there are 2 different sources in the system, but they're all actually binary system. So there are 2 stars which are orbiting each other. We just haven't resolved them yet.
Okay.
So
And that's okay. I'm with you. So that would be a pure
yeah,
binary population.
it's not pure in the sense that well, we're not very sure that it's exclusively binaries, but for the most part, it is a binary population.
Dominated. Okay, good. Okay.
So once coming back, there's one important section which we missed in section 2, which is the differential reddening correction,
Yeah,
Oh, yeah.
which we realize is very, very
very important.
important for this work.
And
Hmm.
Yeah.
at least when
Khushboo,
you
do you
are
want to
trying
take it?
to, yeah, if when you are trying to identify the equal mass binaries, there it is very important because we know open clusters are situated in galactic plane, right? And the
Yes.
galactic environment, and they are very much affected by the foreground dust and all those things. Many paper which comes out, they do not take care of the differential reddening, but we initially did not do it, but eventually we realized that it is very important if we are talking about binaries particularly.
Yes.
And that is why we perform differential reddening correction for these four clusters,
Okay.
particularly for the 6819 and 7789. Initially the binary population we saw was the population was not actually binary population, but that was the highly reddened stars.
Ah, okay.
They were just situated very off to the one direction of the cluster spatial distribution.
Yeah.
So then we just perform the differential reddening, and this method we had developed in our previous paper for the to identify the blue stragglers, because differential reddening can lead to misidentification of the fundamental parameters like ages
Yes. Yes.
and the binary mass population. And recently, when I was working on the star clusters, because I find color magnitude diagram very, very fascinating. So I just look at them, and one cluster I was working on, and I saw that there are two main sequences,
Yes.
and I was very puzzled. I was happy. I was puzzled too, but before confirming anything, you need to perform differential reddening, and that I learned with this paper.
Okay.
So I performed differential reddening correction for that cluster, and I saw there was no two main sequences.
Okay.
The the other reddened sequence was not actually another sequence, but just the highly reddened stars.
Yes. Okay. For whatever reason.
So
Right.
yeah, so differential reddening correction is very, very important for old open clusters because they're interstellar dust and foreground
Yeah.
dust. So for this method, we just fit a isochrone very
Okay.
close to the blue main sequence of the cluster,
Okay.
and then we use the reddening vector, which is well fitted to the um, red clump of the cluster. And then using that reddening vector and the main sequence isochrone, we choose sources which are located in the main sequence. And for this, we use in a spatial distribution, we use, let's say, almost around 25 stars. And we
Okay.
see their position on the color magnitude diagram, how they are distributed. We calculate their mean color and magnitude and
Yeah.
drag that mean value along the reddening vector to the fitted main sequence.
Got it.
So the
Got it.
difference we get, that difference is actually the differential reddening and extinction for that particular star,
Yes.
for around which we have
Cool.
taken 25 stars. So
That's
for
pretty
each
cool.
star, we iterate this process,
Okay.
and we
Okay.
generally we can at the end we get the differentially reddening corrected CMD and the reddening map.
Yeah.
We can iterate this process as many time as we want, but here we just stop for the one iteration. We say that we got the
Got it.
fairly good corrected
Mm,
CMD.
very
As
cool.
you can go to the figure 1.
Yeah, sure. Figure one.
Yeah, so it
Slide
shows
down a
the
little bit. Oops, figure one is up. So let's go to figure one. Reddening maps. There we go.
yeah. So the left figure is the reddening map of the cluster. As you can see, there's a blue and cyan color. So
Mm-hmm.
cyan color is basically the highly reddened stars. You can see the
Okay.
patches,
Okay.
and the
Ooh, wow. Okay.
color, the middle color magnitude diagram, that is the Colander 261.
Mm.
Color magnitude before a differential reddening corrector is observed, and you see in the redder part of the CMD there are many sources.
Ooh,
It looks
yeah.
like they are just the contamination, but we know that MLMOC is quite intelligent. It won't pick many contaminants. So when after differential reddening correction, we
Uh,
see that this even the RGB branch and main sequence is quite well defined now, and
much
there
better.
are just a few sources here and there. Otherwise, these sources which were looking actually scattered or contaminants, they are actually the members and they are just sources. So
Yeah, it
this
really
is the import.
really sharpens up that
Yeah, exactly. And
CMD, definitely. Very cool. Very nice.
so
Very nice.
then after this, we perform the selection of the other cluster population. So first step is to just do the differential reddening correction.
Okay, nice.
And then we again fit the isochrones and determine the ages and metallicity and all those parameters.
Uh-huh. Okay, good.
Yeah.
I'm with you.
Balan, you can take it up now.
Yeah, so thanks. So that was basically like the actually the chronological order in which we worked in the paper as well, where we first just took a look at the raw figures, and then we were like, we've probably got some good, interesting science results. Then we realized that oh no, we have to do differential reddening
Yes.
because when we took second look at columnar 261, I was like, okay, this is a little silly. We should have definitely taken a look at the region to the red areas of the cluster where there are actually quite a few stars which do look like contaminants. And yeah, so when we went back and we did differential reddening, the cluster really sharpened up. All of the clusters did sharpen up. We've got the other figure in the appendix if you're interested. So once we got the new figures, we performed all of the analysis again. Thankfully, it didn't take much time since I had everything ready. I just need to redo everything. So once everything was
Crank again, yeah.
done again,
Yes.
then we iterated over a couple of other calls with all the authors, and then we finalized the paper again. So that was how the development went as well.
There, yeah.
And
Good.
yeah, moving forward to section 3,
Okay.
let's take a look at figure 3, Frank.
Okay.
So in figure 3 is where we have the cumulative radial distributions.
Mass
So
segregations. That's what we're looking at. Okay, mass segregation. And figure 3, CRDs.
yeah, CRDs.
Mhm.
So CRDs are very interesting. So CRDs are what you'd call an ECDF plot. So ECDF plot is the empirical cumulative distribution function. So that's a lot of words. So I'm just going to stick with CRD. CRD. Yeah. So basically, what we want to do is we are starting from the very center of the cluster and we're slowly moving out. We want to understand how many stars of the cluster are within this particular sphere that we're looking at.
Yes.
And so we measure out a cluster radius and we normalize the distance of all of the stars in the cluster based on the not the cluster radius, the core radius. So we have multiple different radii, which we use to describe. That's used to describe the cluster. And so now we're looking at the core radius. So we normalize all of the distances of each and every star in the cluster from the center with its core radius. Then we take the logarithm. So we can see that obviously the distribution shoots up as we get out of the core radius because we're trying to cover most of the members very quickly.
Yes.
But the logarithm helps us understand which populations are primarily located within the core.
Yeah.
So if some certain population is strongly located in the core, then we know that these populations are heavily segregated. And we can take a look at, for instance, NGC 6819 or Berkeley 39. We can look at a massive chunk of the blue stragglers are located within the core. And in the case of 6819, so are the red giants. So
yeah, okay, I see it. I see it.
Yeah, that's like the key idea of the study. And if we look at NGC 7789, most of the blue stragglers are located just after the core. So and in column 261, it's about 50-50. It could be either way.
Yeah. Still.
Yeah, so with this is the primary idea. This gives us a quick rundown, a quick insight into which clusters could be mass segregated with respect to the blue stragglers and which may or may not be. So now we need to do more analysis to confirm or to deny these results. And so that's when we moved ahead to the second result, which is the proper motion distribution. Another thing which we did with respect to these CRDs before we quickly move on is we performed the AD test. AD test is the Anderson-Darling test, and that's a statistical test.
Yes, yes.
Yeah, which is very similar to the KS test, so the Kolmogorov-Shimonov test. And the reason we chose the AD test is because it has higher statistical power especially when we're looking at the tails of the distributions, which is what we want to highlight in our particular study, because the left tail of the cluster refers to the core and the right tail of the cluster refers to the periphery. And we want to look at these two regions specifically as opposed to KS, which focuses more in the center of the distribution. So because we wanted to, like really look at the core of the cluster, that's why we chose the AD test. So the results of that are there in table 2. If we'll get to that in a bit when we talk about the discussion. The second analysis which we performed was the proper motion distribution in figure 4. So
figure 4.
Again, the idea over here was to get a quick insight into the kinematics of the paper in terms of the proper motion. We want to look at how scattered each population is individually. So if the blue stragglers are heavily scattered, then we know that they've got the large velocity distribution. They're just skimming around the cluster. We will perform another confirmatory test for that. But the idea is that, especially in the case of NGC 7789, we see that some of the blue stragglers are just thrown apart in the extremities of the proper motion distribution. But in the case of NGC 6819, they're huddled, they're close to the center, which means they're not moving around as much, which makes sense. Eventually with time, the heavier blue stragglers have settled down. They don't want to run around as much. But in 7789, they're still frantically jumping around. They're all like having fun. They're not as evolved yet. And so when we compare it with the other populations in the cluster, we find that 6819 generally has a very reserved bunch of heavier stars, while in the other cases, they have a fairly enthusiastic branch of heavier stars, which is still running around. So that brings me to the third analysis. This figure was just done with kernel density estimator. So it's just like a contour plot done with KDEs, and that I think that brings it down to like a slightly simpler term, which the broader audience might appreciate. It's a simple KD.
Technical.
Yeah, KD with contours.
That's fine. The 2D calcium.
Yep, and
estimator.
KD estimator. Yep. So then we move on to the kinematic distribution in terms of the galactocentric coordinates. The final analysis which we did. And over here, this is where we wanted to really understand the kinematics of the cluster. And what we did is all of these clusters are fairly far away. And as a result, all of these clusters suffer from very significant line of sight elongation. So if we take a look at figure 5, we'll see that we're completely lost in one of the axes, on one of the planes, because we're looking along that axis. We're completely lost. We have basically no data whatsoever when we're looking directly at the line of sight. It's in the other figures that we're able to resolve any information whatsoever. And as a result, this was a big problem because I was very disappointed that we're not able to find anything in a 3D figure of the cluster. We're restricted to still a 2D analysis now. We did look up different distance catalogs. Bailey-Jones is the most comprehensive one out there. Bailey-Jones 2021. And even with Bailey-Jones 2021, we could not get a good result. So we ended up working with just 2 dimensions. And you can still see in the case of 6819 or Berkeley 39, and even in the case of Columbia 261, that most of the blue stragglers are still, in the core. So that does correlate to the result which we saw in the CRTs in figure 3, that the blue stragglers are indeed huddled up towards the center. And the RGBs follow suit. Some of them are scattered on the periphery, but most of them are still huddled close to the center. And the lighter populations, at least in comparison to these, are scattered throughout the cluster. So they're fairly spread out. So that's how the galactocentric positions look. We also wanted to take a look at the galactocentric velocities. So for this, we cross-matched our sources with other catalogs. So in the case of Berkeley 39, we cross-matched it with, just a moment.
The Gaia spectroscopic data.
We just got with GES and with NGC clusters, we cross-match it with the Wine data set. So they have a massive data set of different NGC clusters. So 6819 and 7789, we cross-matched it with the wind dataset, and we're able to get radial velocity data from that, which
Very,
brings me to figure 6, the last figure.
very nice. Okay, figure 6. Okay, that was position. Here's velocities. Okay, blow that up a little bit.
So in figure 6, we find a small issue, which is that we were not able to cross match as many of the sources as we'd like, especially with respect to the blue stragglers, which are able to cross match only the case of 6819 primarily.
Okay,
But the other clusters, we're not able to cross match as many blue stragglers.
all right.
So we tried to move ahead with what we had with respect to the other populations because we still have a fairly good idea of how the mass is segregated across, how the mass is distributed across these three populations, which allowed us to take a look at the segregation. So we look
Yes.
in the case of 6819 and 7789, which have some very interesting velocity artifacts.
Mhm.
We'll come to this in a bit, but we do still find the primary takeaway is that in 7789, the sources are still scattered in the velocity distribution. In 6819 and in Berkeley 39, all of our regions and the blue stragglers in the case of 6819 are still huddled up.
Yeah.
So
Yep.
we come to our final conclusion that in these two clusters, we do see some very good signs of mass segregation.
Yes.
7789, not at all, and Conda 261 was still on the APIs. So we
Okay.
went ahead and we called it on the intermediate stage. So I'll let
Yeah, because
Khushboo
we're
take
doing
away
this.
because I've been rambling for quite a
Right.
bit.
Right.
So Khushboo, can you please take us through the discussion?
Yeah. So when we compared the sources with spectroscopic data, the problem was maximum of the spectroscopic observations surveys, they don't go below some certain magnitude range. Particularly, Wien only goes down to 16.5 magnitude,
Ah,
and the
okay.
GES is very good. It goes down to 18.5 magnitude. So we were good with Berkeley 39, but in 619 and 7789
Oh,
cases, we just have a few low mass stars. Or
yeah,
so,
good.
and then so as Balan explained, Berkeley 39 and 6819 just show us some signs of mass segregation. As you can see in Berkeley 39, all the RGBs are in the center, and
Yep.
even in the MSTO stars.
Yep. It's
And the
great.
yellow population, which is the main sequence stars, low mass and main sequence stars, they are
Mhm.
fairly segregated. But in
Sure.
6819, since we do not have many low mass stars, low main sequence stars, so we cannot say much about it. But still, we see that RGBs are fairly in the center. Then
Yep.
the MSTOs and the binaries are also seem to be almost, because we have just few binaries. Binaries are also main sequence binaries. So
Okay.
with the cutoff with the 16.5 magnitude, we just have a few binaries cross-meshed. And
Hey.
in terms of 7789, it's a pretty interesting result. We see that many
Hmm.
of the main sequence turn-off stars, they have particularly a higher velocity in the y direction, right?
Yes. Yes.
It okay. So the reason we searched and we did the analysis for 7789, what is happening with these particular high velocity stars. And we found that these stars, which have fairly high velocity, radial velocity, they have high radial velocity and they have larger rotational velocities. We
Ah.
or projected V sin I basically
These
projected
ions. Okay.
rotational velocity.
Uh-huh.
And
Uh-huh.
because NGC 7789, it has an age of 1.6 giga year.
Okay.
So
Okay.
the sources which are on the turn off, they have masses greater than 1.3 solar mass. And
Okay.
we know that 1.3 solar mass is the uh, textbook or maybe well-known fact that below 1.3, the stars have the uh, convective envelope.
Yes.
So
Yeah.
throughout their lifetime, they are losing
Yes.
mass, they are slowing down since their formation. But above 1.3 solar mass, these stars have radiative envelope.
Okay.
And after their formation, they do not slow down much. So they are fast rotators. So all these stars, main sequence turn-off
Uh-huh.
stars, which have high radial velocities, they
Yeah.
also have high rotational velocities greater than 120 kilometer per second,
Okay.
V sin I.
Yeah.
So this is fairly large.
Yes. Cool.
So this indicate that this cluster has the we call it extended main sequence turnoff, like the high rotators.
Yeah.
If you look at the color magnitude diagram also, it is pretty visible. If you
Let's
go
go
to
to
the
that CMD.
figure second.
Yeah, it was figure 2 and the CMDs. Let's go revisit those. Okay, CMDs again. We have to wait a few seconds for the internet squirrels to do their job.
Yeah. So if you look at the CMD,
Yes.
the MSTO part, that appear to be quite broadened compared to the main sequence. If you look at the green and yellow part, you
Yeah.
see that the turnoff of NGC 7789,
Yeah. Oh, wow.
yeah, it's
Yeah, yeah,
quite
yeah.
broadened.
Yeah,
So,
yeah,
and
yeah.
the high velocity stars, high V sin I stars are particularly in the redder direction.
Uh-huh.
Redder direction of the CMD. We have not shown here because that was not the purpose of the paper.
Right.
But
Cool.
these
Khushboo, do you
stars,
think we could show that figure in this call? I was looking up, I was trying to find that figure now. I just have it ready. I think it would
oh,
be
then
fairly
that would be
instructional
a
to show
pretty
it.
good
So,
thing.
yeah, how do I do this, Frank? Do I just email it to you?
No, don't even. So, okay, so we're doing a little impromptu here, people. Okay, so I'm going to
Yeah,
stop
this is
the share
important.
here, and I'm going to
Okay.
give you some sharing capabilities, advanced sharing options. Which I've done this beforehand, but here we are. Okay, go.
Yeah, we did not plan this. Um,
No, this was an unplanned event here, people. It's all good.
so let me share my screen.
Uh-huh.
I have this nice image here. I'll just make it slightly bigger for everyone.
Mm-hmm. I got it. Yes, I see it.
Yeah. And
So this
these,
is a very rough figure, as you can see. Like there are
Uh,
no axes, there are no labels whatsoever.
You,
It
you,
was in
you
a
know
group
this is a
discussion
research
call.
plot when you haven't even put labels on the axes yet.
Yep. So this is within our discussion. We're just trying to figure out what the reason could be. So that's why there are like a massive legend, no axes whatsoever. But I thought it'd be very interesting to show this plot where you can see that all of the rapid rotators, like how Khushboo was talking about, are located towards the redder side. I'll just let you take it away.
Okay.
But yeah.
Okay. Interesting.
yeah. So if you look at the CMD, the blue squares, these
Yes.
are particularly in the redder direction of the CMD, and all the other sources, single members, they are above.
Okay.
And this shows that okay, so in currently people assume that people observe, not assume, they observe that the high rotation velocity stars, because of the high rotation and their inclination, viewing angle and inclination, these sources appear to be redder and fainter than their non-rotating counterparts.
Okay. Okay.
So
Yeah.
with this work, though we haven't shown in the work, but we have discovered that this
Huh.
particular NGC 7789 has extended a main sequence turnoff. Like
Yeah.
it appears that it cannot be fitted with single edge, but it has multiple edges. It give an artifact of but it is just they are all single stellar populations. Just few are fast rotators and few are slow rotators. That's it.
Got it. Got it.
Yeah,
Very cool.
this is what we observed with this work.
Thank you.
So yeah.
Very nice. Okay.
I'll stop my sharing so we can move back to the paper.
And we will go back to the paper, and we were looking at these CMDs. Wait for those internet squirrels again.
So this is what
There
we
we go.
observed for 7789.
Uh-huh.
And for Kulinda 261 is again an interesting cluster where we saw that particularly blue stragglers are highly segregated. Even in the proper motion distribution, we saw that,
Yes.
as Balan explained, blue stragglers are particularly segregated. In spatial distribution, they are segregated. So, but rest of the population, not at all segregated compared to each other. They all appear to be similar.
Okay.
So, this we there is another case, such case for a Mallet 66 cluster, which shows a similar signature,
Yeah.
that the only blue stragglers are highly segregated than the rest of the population. So
Mhm.
the idea could be, when in our previous work, we also seen that the central density of this cluster is quite low.
Oh,
Though the cluster is very rich, central density is not as high as it should be. So therefore, the blue stragglers, they have settled in the cluster center prior to their formation. Because in open clusters, blue stragglers form via binary evolution, mass transfer, and those
right.
phenomena. The
Yes.
binaries are
Right.
massive, they
Right.
segregate in the center faster.
Sure. Sure.
So
Yes.
to confirm, still confirm this result, that how we need to go back to check how blue straggler stars were formed. We either need a radial velocity data to check their binary refraction, or the spectral energy distribution to find
Okay.
if there are any hot companions,
Okay.
which would prove that they have formed via mass transfer, or their abundance analysis. These would require to actually confirm their formation and to investigate why they are in the they are highly segregated compared to the other population.
Right.
And in this work, we find that bug NGC 6819 is actually highly segregated, and Berkeley 39 and then Kulinda 261 and 7789, they are younger, just they are difference in the blue straggler population.
Right.
But further confirm these results for particularly Kulinda 261 and 7789, we would need the radial velocity abundance analysis data, or we probably need to have um, the simulations and body simulations to see
Okay. That'll work.
what is happening.
Right.
Yeah. But all these clusters, which were actually with respect to the blue straggler stars, they were all almost, if we talk about with RGBs, they all appear to be similar or dynamically young, but they are not.
Right. Okay.
They are not. They are at different stages. And it is irrespective of their ages. 6819 is very young. It's 2 gigayear old cluster, but it's highly evolved. Berkeley 39 and Kulinda 261, these are 6 gigayear old clusters, but they are again different evolutionary stages. And
Okay.
7789, which is 1.6
Okay.
gigayear. So it is fairly matches with it. It's a chronological age that it's a dynamically young cluster.
Yeah. Right. Very cool.
So
Very
when we
cool.
come to the idea that it has been proven that blue straggler stars can be used to assess the dynamical ages of globular clusters, and we
Indeed.
have also seen in our previous work that all fairly we can use blue stragglers, but actually to know about a particular cluster, we need to go to their population, and we need a particular analysis like this we have done
Indeed.
for these clusters to see actually what is happening with those clusters.
Okay.
Sometimes blue stragglers can give a false idea of dynamically evolved or young clusters
Yes. Yes.
for specifically for open clusters.
Cool. Very nice. Very nice. Beautiful work. Beautiful work.
Thank you.
Balan, Khushboo, I want to thank you so much for walking us through your very awesome article. Very nice.
Thanks again,
Thank you,
Frank.
Balan.
This is a great opportunity.
Yeah,
Sure.
thank you for giving this opportunity to talk about our work.
Sure. And you kind of touched on it a little bit there toward the end. So let me go ahead and push on it a little bit. And where do you think we go from here, given the published article? So is there additional observations to do on these clusters? Are there additional observations one can do on other open clusters? Just sort of next steps. Where do we go from here?
Okay, so we were thinking to include this result in this work, but we did not. We wanted to check the velocity anisotropy for these clusters.
Okay.
This is generally done for globular clusters.
Yes.
Velocity anisotropy means with compared to the center of the cluster, how the sources are isotropic. The velocity is isotropic in the center, or in the outer direction is the tangential isotropy or the radial isotropy. These will tell us about the is the cluster is really segregating in the center, what is happening with the in the outskirt of the cluster, which
Right.
also gives an idea about the any nearby giant molecular cloud interaction with the open clusters, or what is happening with the surrounding of the cluster, which is not
Oh, the environment. Yeah,
letting blue stragglers to settle in the center, or there is nothing so that they are segregated in the center.
yeah.
So we were thinking to lead this work into that direction.
Okay. Very cool.
Yeah.
Well, that'll be very exciting to see in a little bit. Very nice. Very nice. Balan and Khushboo, thank you so much once again for walking us through your very lovely article. And it'll be really exciting to see this develop over the next couple of months to years, or at least one graduate student trajectory anyway. Very
Thank
cool.
you, Frank.
Yeah. And that will
Thank
do,
you.
everyone. And I hope this made your open cluster astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye bye.
Bye.